Thanks for having me. I'm absolutely delighted to be here. Thanks for the invitation, and very glad to see several familiar names among the list of participants. So, as introduced, I am a. Give me 1 second. I'm an associate professor at Duke. I came here from Princeton, where I was affiliated with the Princeton Edge Lab. My PhD is from Columbia. And over the years, after I spent a lot of time in industry, I worked in industry after every single one of my degrees. Some of the companies that I've had the pleasure of being affiliated with are shown on the screen here. I run the Duke I3T lab, which has 7 PhD students and 1 postdoc, and 2 students committed to coming in the fall. We are a very vibrant group of people. We believe in undergraduate research. We have high school students, so overall, it's a great environment, very dynamic. We're not that far from Virginia Tech. It's a relatively short drive, so if you're welcome to come see us. We would love to host you. We would love to show you what we have going on. Open invitation. We really are not far. I made this drive very recently for the DARPA PI meeting, and it's very doable. So yes, please come. So we work on mobile systems broadly, but specifically we work on next generation augmented reality, where our core research direction is in making augmented reality context aware, respond to the state of the environment and the state of the user, and reliable. So we talk about augmented reality that you would truly trust. It's not a toy for a game application, but rather augmented reality that you would trust in guiding you in working with a large and dangerous robot, or having as part of surgery that's performed on you. We are a computer systems group. We do not work strictly on graphics, for instance. We specifically work on platforms that support next generation AR experience. So a lot of our work is in edge and cloud support for augmented reality, in edge AI that enables some of the core next generation AR capabilities. And we do some work on sensing. We started a line of work that integrates augmented reality devices and robots. So I'll mention this briefly soon. So overall, we are very much a mobile systems group that works on next generation AR. And I wanted to make it clear that specifically this presentation is about AR. So it is about cases where where you take a real world and you add virtual contents to it. And this is important in context of this presentation, since the core of our approaches is about that. Our approaches are about comparing the state of the real world and the state of real world with AR added to it. So what I describe in this talk is specifically for augmented rather than virtual reality. Augmented reality it's been an interesting field for the last couple of years. Some of the devices are getting older. HoloLens and Magic Leap, for instance, are not state of the art anymore. On the other hand, a number of interesting devices have been coming on the market. So here in the top left corner, you have the Apple Vision Pro. It made a lot of noise when it first came on the market, but the adoption hasn't been all that great. But overall, it's a great device and an example of what modern AR headsets could accomplish. At the bottom on the left, this is an example of Samsung Galaxy XR headset. Came on the market in the fall. Great graphics, very interesting headset. You get access to eye tracking capabilities in it, which is helpful for research. One thing that has been emerging recently is this AR via smart glasses. And some of the models that are currently on the market are shown on the screen. A lot of investment is going into the space. The models that you see here are only some examples of what's available. Most analysts expect exponential growth in the space. You may ask, how this is different from Google Glass. That was 10 years ago and it didn't go anywhere. And the difference is that currently we have this very strong AI backend to essentially the same form factor. That nowadays you can take the sensor feeds from those devices, send them to powerful models for processing, and get something that is actually very useful. And this is why a lot of people in industry are really betting on this form factor. The displays there aren't great, of course. They're nowhere near what you would get with a headset. It's not even in the same category of devices. Yet these are it's a very interesting development that backend AI integration is making them helpful and useful and something that people would actually wear despite the shortcomings in graphics. I'm not discussing it in this talk, but if anybody is interested, we have a line of work on detecting that somebody is wearing these smart glasses. This is in context of that if a student is wearing them to an exam, for instance, you really want to know that they're doing that. So I'm happy to discuss that offline, and the paper is on the screen. It's publicly available. So my group builds a lot of AR applications. Some of them are on the screen here. So the very top left corner is our example of augmented reality for guiding CPR. So here you have this if anybody has done some CPR training, you would have seen that chest compressions in CPR, you do them differently than what it looks like in the movies. You have to press harder and much more frequently than you would expect. So this app uses AR to guide users on the depth and the strengths of CPR compressions in CPR. It's here. To the bottom is an example of an app we have built for studying user attention, and it is an app where AR is used to help users solve a Sudoku puzzle. So here, if the user goes along solving a physical puzzle, if they make mistakes, our system identifies that they have made the mistakes and it offers correction. So there's an element of handwriting recognition that's built into it. To the top is a classical example of AR-based assembly guidance, very interesting, helpful use case. And to the bottom is one of the examples of our work on AR in healthcare applications. So this is a big application space. Here specifically, this is a fairly classic use case of augmented reality for EVD insertion. So where a small catheter needs to be inserted into the brain of the patient to release intracranial pressure. And the trick here is that the opening in the skull that's made for this procedure is very, very small. You see these little dots here. And so effectively the surgery is performed blind, that the surgeon is trying to reach the right point via a catheter, via this very small opening. So here augmented reality can be very helpful in showing the surgeon where specifically they're supposed to be headed, what specifically they should be targeting. This is especially helpful for junior surgeons and especially helpful in cases where patient's anatomy is not standard, where classical approaches that they would have learned for targeting where the ventricle would be under normal circumstances are slightly different for this specific brain for some reason. So in this case, AR guidance is very helpful. We've also been doing a lot of work. I'm very excited about this line of work, augmented reality and robotics. So this is where AR has very nice properties for serving as a part of interfacing with robots. One issue with the robots is that we do not know their intentions normally. We do not know their intentions, we do not know their perception. And AR is a very natural interface to bring out that information. So for instance, if you're working with a robot and you're in an environment where a robot makes its own inferences about the state of the world. So the robot looks at the chair that's next to it and says that this is a chair. Then in augmented reality, you can show those robot-generated labels and for the user to oversee. So this is a very nice capability, very important. We've demonstrated that elements of that with different types of robots, aerial, wheeled, and this is our favorite toy, the robot dog. That's very fun to work with. The one element is that you can very readily see what robot infers about the environment. An interesting twist on that is that you can use AR to visualize what robot perceives about the user. So that let's say that the robot believes that the user will walk forward. That is something that you can show to the user in augmented reality, and that informs the user action. So overall, this is a great way of facilitating human-robot teaming by showing the state of the robot, inferences of the robot, but also robot's ideas about the state of the human. We have a number of we're working on this very actively. We had a couple of recent demos, and overall, we're very excited about the promise of this work going forward. Now, augmented reality, I work on mobile systems, and in mobile systems, there is a general understanding that augmented reality is the future. That mobile computing state of the art is a smartphone, and smartphone it's clearly not the future. So the future is elsewhere, and a lot of people believe that the future is AR. And here are a couple of quotes from technology leaders that convey this belief in this technology. But then it's also worthwhile stepping back and thinking, well, what are the limitations? This is the vision, so what else is there to be done to enable this vision? And I have some examples of limitations on the screen. Let's say headsets, they're still too heavy, definitely for sure. One specific thing that I want to discuss today is security. And there is a lot to that. That augmented reality is a device that you wear on your head. It fully modulates your visual perception. So what the device projects to you is what you get in terms of vision. And there are very obvious challenges with that. So let me take a step back and talk about the let's call them reality distortions. Given that you put that device on your head and it is between you and the real world, what dangers come with that? You see the examples of three classes of distortions on the screen here. So you could be in a situation where augmented reality is simply making parts of the scene harder to see. So this is your basic visual clutter, and that's to the left of the screen here. Too much information, perhaps information that's irrelevant. Overall, just clutter. To the middle is an example where you get into more dangerous situations. This is where virtual contents could be blocking elements of the real world. We have demonstrated that with optical see-through and video see-through AR headsets both. So here you see this is on the HoloLens. This is where a visual is starting to abstract text in the environment. And here is an example on an Android. This is where this little sparrow is starting to abstract user's view of the knife at the edge of the table. So this abstraction of the real world. And this has obvious safety implications, since this is, again, very readily implementable, very easy to do on all sorts of platforms. And you can use that to abstract, pedestrians, safety signs, all sorts of things. So clearly a very important consideration. The case on the right is the trickiest one of all. So this, where you're actually blocking users' view of key elements of the real world, that requires you to add, let's say, sizable visuals and to interact with key elements of the real world in a fairly blunt way. You can also be in an environment where your virtual content that is added to the scene is fairly small, but it's strategically placed to change the meaning of the scene. So the example is here. So this is where we are showing how we can add very, very small virtual elements to change the digits on the clock. And here's an example of a similar attack that shows how you can change the meaning of the sign on the road. And more examples of these kinds of, we call them information manipulation, since they really are about changing the meaning of information that the user would get from the real world. So some examples are here. So in this column to the left, here's the case where you are adding a virtual element and it changes the affordances that the user would see in this world. So here, this is actually a one-way road, but if you add this U-turn element that suggests that a U-turn is allowed where it is not. In the middle here, this is an example where you add information in AR that contradicts the state of the real world. So here you have this example of a fun game character that invites you to get into a certain physical space, despite the fact that there are danger signs that are placed next to it. And this virtual character is very exciting and enticing. So that could represent a danger. And in this example, we take a no parking sign and we put you can park here. So this contradiction of virtual and real. And in this column, the examples are where you just downright change the signs in the real world. So you reverse an arrow. This is with augmented reality, or you change the meaning of a danger sign that is posted. The approach that we are using for detecting all of these types of attacks effectively boils down to the following: that we take the camera feed from the AR device, and we take the augmented reality frame that is generated by the AR app. So this is shown to the left of the screen here, and then we try to infer whether addition of this virtual content has changed the meaning of the real world in an important way. Now, I really want to make it clear that we're not simply detecting that AR content has been added to the scene. We're not running a diff to see that a new element has been placed in the scene. By definition, augmented reality adds things to scenes, so there will always be some element of scene modification. What's important here is whether this modification that has been done constitutes a danger. So does it actually change the meaning of what the user would perceive in an environment? Does it simply, so in this example of reversing an arrow, you have a problem if an AR device tries to reverse the direction of an arrow. If you are using AR to highlight that arrow, arguably you have no issue. So this ability to make inferences about changes of the real world that is semantic, that is informed by what specifically is happening in the scene is very important. And so we want to make a distinction. We want to have a set of methods that oversee AR apps that have this level of semantic abilities. At the same time, ideally, we want them to run fast. So ideally, we want to see that virtual content has disrupted the real world, and we want to infer that this disruption has happened relatively quickly to enable disruption mitigation. And I just jumping ahead, we're doing quite well on being able to detect the disruption, but there is work to do on the latency part of this. And now we've tried a million of approaches to being able to do this kind of inferences of what AR content does to the scene. So I'm very happy to discuss a number of approaches offline. What we effectively discovered is that statistical-based methods, they don't give you anything, since a lot of modifications that truly change the meaning of information in the scene are actually really small. So if your method detects that big things have been changed in the environment, those methods aren't a good fit. We have tried a number of classical ML methods, and we really have discovered that the latest and the greatest, which are the vision language models, really are the right tool for this job. That they offer us this ability to get to the meaning of the change of the scene and to evaluate it. So I'll give you an example of a couple of attack detection approaches that we have demonstrated that use this principle of assessing the change that has been made to the scene with vision language models. So our first example is with abstraction attack detection. So this is the case where virtual content abstracts users' view of important parts of the scene. And the diagram that we have created for this is on the screen here. This is our system diagram. I want to walk you through an example to demonstrate the steps of the solution. So let's say that you're a user who walks along this wall. If you've been on Duke campus, this is our Duke stone. We're very proud of it. Those the walls that look like this are a feature of our campus. And so the user walks along. They're using an AR app. What's actually in the view of the user is that there is this wall and there is a sign there that is arguably important, that this is a fire lane, you should not park there. What the user is seeing, however, is this kind of AR view where this sign that's there for safety and for guiding users is not readily visible to the users. So what our system does in this case is that we stream both the real frames and the frames where they are contents added to the edge server and then to the cloud. And when we set the real frame to the cloud, this is where we run a high-end reasoning model such as GPT. And what we ask that model to do is to tell us whether there are important objects in the scene. That model then returns to us the list of key objects just as textual description. In this case, that would be a no parking sign. And that those identities of key objects that are in the scene are now passed on to the edge server. Then, so effectively what we have on the edge server, what we get from GPT is a set of object names that correspond to what the important objects in this scene are. Then we go along, the experience continues. The real world and the virtual content frames are streamed to the edge server. The edge server does two things. One is that it identifies where the virtual contents are in the scene. It just compares this, and from that we get the mask of the locations of virtual contents in the scene. And this is to the very right of the screen here. The other thing that the edge server does is that it takes the real world frame and we use a smaller open set object detection model such as grounding Dyna to identify where the key objects are in the scene. So this model is prompted with the object list that was populated by a higher level model and with a frame that you have received from the real world. And that gives you a mask of where important objects are in that scene. So this is shown here. So now we have a mask of where important objects are. We have the mask of where the virtual contents are. So we simply compare the two masks, and this is what tells us whether virtual content abstracts users' view of important elements of the real world. What I really like about this design is that it really takes this high-end reasoning vision language model out of the loop, that we do not rely on it for frame-by-frame inference, and that reduces the latency of the solution dramatically. Our highlights of our results are shown on the screen here. We created a special dataset for this for testing the abstraction attack detection. The results for our method and a number of comparisons are on the screen here. So our method is Vidar, and you can read the numbers on the slide. I wanted to note a couple of things here that the attack detection accuracy that we are getting in this work is quite good. We get to 92%, which is very promising for real-world deployments. If we use models that are less capable, the performance drops. That's, of course, expected. Prompting is important for this case. This is very standard with all work that relies on VLMs or LMMs. Here, if we tell the model to be on the lookout for safety critical objects, we get better results than if we just ask it to, let's say, tell us what the important objects in the scene are. And the latency results here are quite good. So we get to under 1 second latency due to this separation of edge and cloud capabilities. It's not enough for instantaneous correction of AR actions, but that's a really good number for creating oversight systems for AR experiences. And just as a side note, so we did this work early last year, and this December we reran the results with newer models. Some of the results that you see are on the screen here at the bottom. What's encouraging is that back when we started this work, GPT's performance was clearly above the others, while currently there are other models that are also very good at this task, such as Gemini. It was also interesting to see that if we take the newest version of GPT and we use the prompts that we used before, the performance drops slightly. On the other hand, if we go look into it, see what specifically is happening, we are able to adapt our prompt to get to a higher level of performance. And what this suggests is that work of this style that relies on VLMs needs to be, it requires maintenance. That every time that new models are coming out, systems like this one would need to be recalibrated and their performance carefully tuned to avoid this performance loss that happens due to model updates. So we got to very good latency numbers here, and that allowed us to show some demos of this work since they become quite responsive. This is the demo we showed at ISMAR in 2024. This is where it's Android-based, and this little sparrow is blocking user's view of a knife at the edge of the table, and the sparrow is made transparent. And here's an example that we built with a Meta Quest. This is where this Duke Shield, virtual Duke Shield, is going to block user's view of a stop sign, and we will make that transparent. Yes, so very very nice latency results that allow for this level of interactivity. We've also been conducting another line of work that is specifically not on real-world abstraction, but on information manipulation attacks. And this is where examples of those attacks are on the screen here. That this is where we are altering, let's say, digits that are around the user or text in the space of the user, or we're changing the symbology, such as reversing the arrow on a one-way sign. An interesting specific class of this attack is where we're not even touching any critical part of the scene, but we are adding new elements to the scene that change its meaning. So an example of this addition of this U-turn arrow. And in this case, we have, unfortunately, we don't have this nice separation of edge and cloud. Here we have a system that relies on high-end VLM to assess whether an attack has happened, and this increases our latency. So the system is shown on the screen here, and the results for highlights of the results are on the screen here. That overall, our similar takeaways to the previous work, that our overall accuracy is really strong, that this suggests that you can use this approach in real environments and have it serve as a useful intrusion detection system, shall we say, that it can be a very helpful AR experience oversight method. We get worse on some attacks than on others. We do really well on detecting text manipulation, for instance, and much worse on cases where we are adding new elements somewhere else in the scene. So this work received the ISMAR Best Paper Award last year, and I think that it's actually for a very good reason, that augmenting reality, modifying your world without your knowledge it's a sci-fi trope. There are books and movies and all sorts of things that are based on this idea. Here, for instance, this is, I don't know how many of you watched this. This is a Black Mirror episode, Man Against Fire, where somebody who is wearing AR contact lenses has people next to them transformed into terrifying monsters. So this is again, it's a sci-fi trope. It's decades old, but finally, with these models that are emerging, we're finally able to have an oversight of that. So we're finally able to detect that. So we got a lot of confidence that VLMs are the right solution for this problem. So we've been expanding on the work in a couple of directions. So far, all that I've demonstrated is about real world and virtual world disagreements. There's also an interesting possibility here of evaluating whether virtual contents contradict each other, whether two different apps are telling the user different things. Examples of some of those attacks are on the screen here, and note that these are what's interesting here is that these attacks contain a combination of symbology and text. And in this case, we didn't create any kind of special, dedicated, interesting oversight system. We simply tested whether leading models can detect when this happens. The results are on the screen here. The results are, again, quite good. We get to the level of performance that suggests that models are capable of that. And but of course, the latency is still an issue, as is the theme in this work. And our ongoing work is where we are not only evaluating the virtuals that is presented to the user, but we're starting to bring auditory contents into the fold. So now I don't know if you can hear this. Probably not.
Please be aware of the toxic material.
So effectively the attack here is that you receive visual AR guidance and you receive auditory guidance, and that guidance could disagree. So in this case, we are starting to employ large multimodal models to oversee the auditory and visual experience of the users. So we have a data set of MetaQuest 3 videos across a number of scenarios. Examples of what's in the dataset are shown on the screen here. So for instance, one case where is here to the top right, where the audio is telling the user to take the yellow bottle, but the AR visual is pointing the user to the purple bottle. Or here in the middle, this is an example of where understanding of spatial requirements becomes important. That the audio is telling the user to adjust the toy clockwise, while the visual experience is showing that this should be done in the opposite manner. So these are the type of inconsistencies and AR experience manipulations that we're currently studying. And we're very excited to start working with auditory part of guidance, since for if you move to the smart glasses form factor, especially audio becomes very prominently featured there, given the weaknesses of the displays. For detecting these attacks, again, we created this is our system diagram, and our accuracy numbers are on the screen here. So overall, again, very promising, very very great potential for serving as an oversight for AR platforms, and the latency isn't quite there yet. So I'm happy to share the preprint of this work with anybody who is interested. Now, now I hope I convinced you that LLMs are very powerful tools here. That they can detect AR content interference with the real world. That's their real strength. That if you place this teeny tiny virtual content, in some cases that's fine. In other cases, it really changes the meaning of the scene. And this is um, where these tools truly shine. Now, they are imperfect proxies for human perception. They do worse on spatial tasks than on other tasks, and they have several other quirks. Happy to discuss that offline. There is a whole number of scientists that are currently studying that level of behavior. So I'm very optimistic that we will have they will never be perfect. They might not be reaching spatial capabilities of humans anytime soon, but we should have enough understanding of where they fail to be able to use them for this kind of intrusion detection AR oversight applications. The shortcoming that I mentioned several times is latency. And another one that I didn't quite elaborate on is that these are very computationally inefficient systems currently. That I've described methods that you take a frame and you make inference on that frame. In the real world, if you have 60 frames per second, then that's 3,600 frames per minute. And we the amount of information that you need for inference here is very large. So you go far beyond textual inference. You need images. You perhaps need multiple images. And this is where the exciting part is that there is a community of people who are working on solving these problems. That I'm happy to discuss some of those ideas offline. There are ways of doing frame selection. There are ways of doing compression of LMMs so that you have options that solve easy cases and only send up the most difficult ones to the high-end LMM. All sorts of options. I'm very optimistic that we can bring the complexity down. And as a closing thought, I wanted to say that so far, all that I've discussed is about security. But LLMs can do more than that. For instance, if you are in a situation where augmented reality experience is telling you to do something that's nonsensical in context of your scene, that can be detected. Or if you're using them or if your AR experience is giving you guidance that's socially unacceptable, there is probably a way of using LMMs for that. So I'll stop here, and we have a little bit of time for questions, but I'm happy to take a lot of this offline as well.